Okay, so fundamental theorem of calculus. This is it. This is section 4 that we're going to do before the final. And so if this is the fundamental theorem of calculus, right, then you know it's fundamentally important, right? So let's go back to a continuous function f, right? So if f is continuous on the interval AB, then we've already established the fact that if I integrate little f of t from a to x, then its antiderivative is capital F of x, right? So this is the antiderivative, capital F, which means if this is the antiderivative, if I consider just that function capital F, that function has a derivative at every point on the interval a to b, right? Like that's where it came from. It's the antiderivative of something, so it has a derivative of every point. Not only that, when I take capital F of x and I take the derivative of it, right? Then that's the derivative of the integral, and that's just f of x. So this is the fundamental theorem of calculus, part 1, okay? Like it has parts, okay? So another way of writing it is f of x, right? Little f of x is equal to the integral from a to x of f prime of t dt. Okay? So basically, this integrand here, right, is the derivative of f. Yeah. So the f out here is the antiderivative of this. So to go out here, you take the antiderivative, and then when you take a derivative of this, it's that. So this is the derivative of that. Let's take some, no, this is a definite integral, so no c. Let me talk about a couple more. So let's take a look at how this looks. This formula here, or, you know, where this integral is going from a to x. So this, the lower bound, is a constant. The upper bound is a variable. Do you see how this is placed? The upper bound is a variable, the lower bound is a constant. So let's take an example here. Suppose I had d dx, the derivative of the integral from a to x t squared dt. Okay, we're going to go in parts here. This is equal to d dx of the integral of t squared, right? We find the antiderivative is t cubed over 3, right? From what to what? From a to x. This is the derivative of, now let's evaluate that like we were doing in the last lesson. X cubed over 3 minus a cubed over 3. Is that right? Hey. So now I want to find the derivative of the antiderivative. When I do that, what happens? When I take a derivative of the first term, the 3 will drop, so it'll be 3x squared over 3, which is just x squared, minus the derivative of a cubed over 3. That's just a constant, so the derivative of that is what? 0. So I just get x squared back. You see that? I took an integral of t squared, then I took a derivative of it, and I got the same function, but the independent variable has now changed. Okay?
Do you have to do all that? Or
No, no. We have to understand the concept, but I'll show you how to do it later. Yeah. Because this was the derivative. I mean, this was the integral. Now I need to take a derivative of this.
Wait, how'd you get a? Because it's x to n a, so you need both. Okay.
Yep. And then derivative of this is this. Derivative of this. This is a constant. A cubed. A is a constant, like 2. 2 cubed is 8 over 3. That's just a number. It's just a constant. The derivative of that is 0. Okay? So that's an example.
Fancy way to get back what you already
Exactly. That's what it is. But in the interim, we change our variable from x from t to x. So now, the reason why we got what we got is because this lower bound was a constant, right? And so here, when we plugged in a to x, we plugged in x, we got variables. Then when we plugged in the lower bound, it was a constant, so the derivative became 0. Okay? We could not have gotten x squared back if this bottom limit was another variable. So if it was like x over 2, right? Then we would have plugged in another variable and we could not have gotten the original back. So all this is dependent on the fact that that lower limit is a constant. We're cool? Okay. So here I have y equal to this integral. Now I need to find the derivative of this integral. Okay? Derivative, integral. Integral is antiderivative. Derivative of antiderivative is the same function, but with the new variable. All right? So let's do one. So dy dx is just d dx of 0 to x, 1 over 1 plus t squared dt. If I take an integral and then take a derivative, I'm going to get the same function back with the new variable. So it's just 1 over 1 plus x squared. That's it. That's it. Okay? That's it. It's just showing that one is the antiderivative of the other. Okay. So this one here, dy dx, and I do want you to show some, like some work like this on homework especially. Negative is the derivative of cosine t dt from negative pi to x. Negative pi is a constant. X is a variable. This is just negative cosine x. That's it. Sorry. Negative cosine x. I don't know. It's just cosine x. Sorry. Okay. Next. Now look at this. Now I have 1 to x squared. It's no longer 1 to x. And here there is a difference, a very clear difference. Here we have to use the chain rule. So basically here's how it works. d dx, so dy dx is d dx of 1 to x squared cosine t dt. Now, this is going to be cosine of x squared. But later, remember like in this step here, right? Now I have cosine of x squared. When I take a derivative of this, I have to have a chain rule as well. Remember, because I'm taking a chain rule. So it's times 2x. All right? So this is going to be 2x cosine of x squared. All right? Here, dy dx is equal to, I'm just going to plug it in this time. It's going to be negative 2x cubed minus 5 times the derivative of this is negative 2. So finally, negative 2x cubed is negative 8x cubed times negative 2, it's 16x cubed plus 10. Okay. Okay, now look at what's changed. The lower limit is a variable. So imagine this, but switched, right?
The negative.
So now we have to take the negative. But what you do first, this is important, is first you say y is the negative of the integral from 5 to x, 3t sine t dt.
Wait, you don't switch, but oh, you did switch.
Okay? So now dy dt is just the negative of 3x sine x. Okay, now, huh? No channel because it's just to x. Okay, now take a look at this one. I'm going from a variable to a variable. Here, I need to split things up. So, here's what I'm going to do. I'm going to rewrite y as two variables. Okay? What I'm going to do is, so I have 2x and x squared, right? Between 2x and x squared, which is the smaller value? It's 2x. Yeah. So now, can you put your phone away? So now, what I need to do is, I need to have one integral that goes from 2x to 0 of 2 plus e to the t dt, and then another one that goes from 0 to x squared e to the t dt. Okay, so I split it up from 2x to 0, from 0 to the next one.
Well, what happened to 2 plus?
Oh, 2 plus e to the t. I'm so sorry. 2 plus e to the t. But now, I have a problem with the first one because the variable is in the lower bound, right? So I have to take the negative. So y is the negative from 0 to 2x of 2 plus e to the t dt plus from 0 to x squared, this. So, dy dx is negative 2 plus e to the 2x plus, times what? Chain rule. Times 2 plus 2 plus e to the x squared times 2x. Okay? Questions? And then you can write this as, we can factor this, let's say. And we can take out 2 plus e to the 2x. And then what do I have left? 2x minus 2. So, different forms of writing it. Again, if this was like multiple choice, they would factor it out in different ways. So
Wait, but
prepare
one's x squared and one's
to do it.
2x. So you can't do that, right?
Oh, no, you can't do that. I'm so sorry.
I was about to.
I'm so sorry. We can factor out a negative 2, though.
Yeah, so the 2x. Oh, okay.
Mm-hmm.
Can you do part B of example number 2? Can you fully do it out? Because you kind of.
Just for that one, I was just confused why it's 16 is like the same pattern.
I don't know.
Why is there the negative in there?
This one is negative 8x cubed, right?
I'm just confused why there's negative 2. Is least what you did like for those ones is that you have the original function with the place value.
Yeah, but this is negative 2x.
Right.
So negative 2x comes in here. And then negative 2x comes in here, right? So I have negative 2x cubed minus 5 times chain rule. The derivative of negative 2x is negative 2.
You got the beta, or?
I did.
Okay. Yeah.
Yeah? Eli, are you okay?
Yeah, because it's the exact same equation as inside the integral, except now you have to plug in whatever x is.
Because afterwards you have to take a derivative. Right. So, fundamental theorem of calculus, part 2. Part 2 basically says if f of x is continuous at every point a, b. Oh. Then if I have a to b of f of x dx, then the integral will just be equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. You didn't know this, but you were doing this yesterday in your homework, and you never knew that it was called the fundamental theorem of calculus part 2. Okay?
So it's the same thing. Yeah.
Pretty much the same thing. And it goes from here, like it's got the similar setup of what we did in that very last problem, part B. This is also called the integral evaluation theorem, and so on. So in other books, you might see this as the integral from a to b f prime of x dx, right? So if you take an integral of the derivative of something, you now have the antiderivative evaluated at b minus the antiderivative evaluated at a. So again, back and forth, when you have an integral, all you're doing is evaluating, or you're finding the antiderivative. Okay? Okay. So take a look at this one. Evaluate each integral, right, using part 2 of this. So here, when I find the antiderivative, I get 4x plus 2x. Now, talking about the placement of these brackets, you can either say, okay, so this is evaluated from 4 to 6, or when it's more than one term, ask yourself, what is the 4 to 6 applying to? Like, what does it apply to?
Why is it 4x plus 2x?
Sorry, it's not 2x, it's x squared.
I really want to understand that. How did you get 4x plus x squared?
Okay, I'll explain in just a second.
Yeah.
So when the bounds 4 to 6 apply to 4x and x squared, right? Put those terms to which the bounds apply into brackets, and then you can go from 4 to 6. Okay, the way we got this was what we were doing yesterday. It's the antiderivative. It's what function, when you take a derivative, gives you a 4.
I thought you would do e to the u equals, or I thought it was, you had to do, since 4 plus 2x is also the first.
No, you do it, term by term by term. This is the first property where if you have the integral of f plus g, it's the integral of f plus the integral of g. Okay, so this is now, when you plug the 6 in there, you're going to get 24 plus 36, minus when you plug the 4 in there, 16 plus 16. So altogether, it's 28. Yes, you do. That's chapter 6.
So can I just ask you a tiny, it's like a super quick one. It's just the value of x, like from 1 to 2 of x cubed plus 2x plus 4 over x.
Is that part of the homework?
Yeah.
Let's talk about it later.
Are we going to go over today?
Yeah.
Okay.
Okay.
Yeah.
Let's do this now. So the antiderivative of e to the x is e to the x, evaluated from -1 to e. So this is just e to the e minus e to the minus 1, 1 over e.
Why do you mean subtractive?
we always subtract upper bound minus lower bound. It's always f of b minus f of a. Right? Fundamental theorem of calculus part 2. F of b minus f of a. Here, okay, so we're going to have, this is just the power rule. Plus x. So now, all of this applied to the bounds, right? So it's negative 1 to 3. So this is going to be 81 over 4 plus 3 minus 1 over 4 minus 1. So that's 80 over 4 plus the 2, it's 24.
So we don't have
No C. So here, okay, so here's what we're going to do. We have x to the 3 over 2. The new exponent will be x to the 5 over 2. We're no longer going to divide by 5 over 2. We're now going to just say that's just multiplied by 2 to the 5th, right? That goes from 0 to 4. So this is 2/5. 4 to the power of 5 over 2 minus 0. So what is that, right? That's the square root of 4 to the power of 5. Right? So that's just 32 times 2, 64 over 5. Okay, next one. Here, 5 pi over 6, pi over 6 to 5 pi over 6 of negative sign. The antiderivative here is cosine of theta, right? Because the derivative gives you negative sign, so this has to be positive cosine. And we're going to go from pi over 6 to 5 pi over 6. Cosine 5 pi over 6 minus cosine pi over 6, right? These are your root 3 over 2's. So negative root 3 over 2 minus another root 3 over 2 is negative root 3. Yeah. All good? Okay. So look at this next one. You're like, oh my gosh, what are we going to do? We're going to multiply we're going to square it, right? So we're just going to rewrite this as the integral from negative 1 to 0, x squared plus 2x plus 1 dx. Now, I can integrate this, x cubed over 3 plus x squared plus x.
Is there no way of integrating it from how it was with x plus 1 squared?
There is, that's next chapter.
Can you not do the same process that you add?
It's not the same. It's not the same
Right.
as in, yeah.
Why does it then say over here that?
If it's homework, let's go over it later.
No, it's not. Why does it say that u to the n equals u to the n plus 1 over n plus 1 if we can't do that for this? It's only when it's a single thing.
It's next chapter. It's a different process. Yeah. So here, there is a way. Of course there is a way, because the world can't function with just simple functions like this, right? It's all, yeah, it's all like complex nested stuff. So now when you plug in 0 here, we're going to get 0 minus negative 1/3 plus 1 minus 1. So at the end of the day, it's just 1/3. Yeah.
For D, even though it's one term, we still use brackets, but like for E, we didn't. Does it matter?
For D?
Yeah.
No, it doesn't matter. It was choice, completely choice. I could have done that way as well. Okay. All right. Finding total area. Okay. So to find the area between something like this, right? This is 3x squared minus 3. Okay, so take a look at what you have. You have the parabola looks like this. If you want to find the area between this and the x-axis, right, it's all the shaded regions. So you see here that you've got one part where it's positive, another part where it's positive, and then you've got the area here which is negative. Okay, so the way in which you have to do it is you have to find the points where this graph crosses the x-axis and where the function changes between positive and negative, right? So at these points, the function changes from positive to negative and then from negative to positive. So when you look back at the steps here, you have to partition your interval with the zeros of f, just like I've done over here. Then you have to integrate f over each subinterval separately. So 1, 2, 3 integrals. And then you have to add the absolute values of the integrals. Because if you want the total area, right? This is going to give you positive, negative, positive. But if you want, like if you're looking for, let's say, how much paint you need to buy, right? You're not gonna, that negative is gonna mess you up because it's gonna leave you with less paint to buy. You see what I'm saying? If you want the absolute value of the areas, then when you do the integral, you have to take the absolute value of the integral. So just add them all. Am I making sense? Okay. So correct. It's like distance versus displacement, right? Yeah. Distance versus displacement. I could walk back and forth 30 paces, but if I've gone to the same spot where I started from, my displacement is 0, but the total distance I've covered is 30 paces. Okay? Okay. So again, okay, so to find the zeros here, we're going to say 3x squared minus 3 is equal to 0. X squared is 1, so x is plus or minus 1. All right? So now, check out what we're going to do. This first integral is from negative 2 to negative 1 of 3x squared minus 3 dx. Plus, that second integral is from negative 1 to 1, 3x squared minus 3 dx. But this, because it's in the negative region, I need to take an absolute value of the whole thing.
Can you just flip the 1 and the negative 1? Like, reverse them and then kind of bring positive? You know?
I mean, but that, you can do that, but then, it doesn't always, like there are cases where, like, hang on, I'll talk about it in a minute. Plus, you're going to go from 1 to 2 of 3x squared minus 2. Minus 3 dx. So this is the total area. Okay. Yeah. So then, you do your integral and you solve. So this gives you 4 plus the absolute value of negative 4 plus 4. So together, that's 12. Okay. Now, this concept of taking the absolute value, right, is something that's like fundamentally based in here. So afterwards, when we start talking about displacement, absolute value, distance, displacement, and then like net change and all of that stuff, you're going to see that this absolute value has a lot of importance, right? And so when it's something where you don't know the bounds, then like you can't just ignore that absolute value. So it's something that I need to ingrain from now on. For this problem, yeah, you're just taking the negative of it. You could have done it. But there are going to be cases where you don't know the bounds. You know, like it's a whole situation. Huh?
Because then you subtract that part.
No, absolute value of like all of it.
But you only need to when
You only need to do this one.
you only need to when it's negative.
Yeah, but
Right? Yeah.
so we didn't know the bounds always. So
Huh?
you said like we didn't always know the bounds.
Yeah.
Wasn't it-
Well, you'll see the different problems. Okay. So I have one other thing to say. Let me say one other thing. Okay, look at this region here. You can see how it's symmetric around the x-axis, right? So this one here, you can also split it up so that, you know, like you go from 0 to 1 of 3x squared minus 3, because it's so much easier to evaluate something at 0 than, you know, from negative 1 to 1, right? Because like when you do this, half of it will just be minus 0. And then you can multiply it by 2. Okay, so these are definitely like tricks you could do. When something is symmetric around 0, around the y-axis, you could go from 0 to 1 of them, because then half of the evaluating will just drop to 0, and you just multiply by 2. Okay? Because it'll be minus 0 versus minus something else. Yeah.
Why did you only use like the bounds of negative 2 to 2?
That's what it says in the problem.
That's what it says in the problem. Okay, so this is how we do it analytically. And then to do it on your calculator, you have to plug, if you want the total area, right? Not just area, but total area. Numerically, using your calculator, you have to find the derivative of the absolute value of the function. Okay? So later on, when we're talking about total distance versus displacement, this is it. This is what we're going to do, right? We're going to take the integral of the velocity or the absolute value of the velocity, and that's going to be the difference between one or the other. All right? So, go ahead and plug this in. I want to see everybody plug this into their calculators.